Welcome to this afternoon's colloquium that will feature a excellent scientist and very good friend, Stella Offner. And so Stella has a very interesting life story, which I'll tell you just a tiny little bit of, and then I'll tell you the most important thing about Stella. And so the classic, it's not the belly dancing Stella. I was going to leave that out. Anyway. Anyway. So the sort of classic introduction is that she grew up in a log cabin. Okay, it wasn't a log cabin, but it was in rural Pennsylvania. And then she went to Wellesley, and she majored in physics and math. And then she took some time off and went to Oxford. And then she went to Berkeley and worked with Chris McKee and Richard Klein and got a PhD in physics. And then she came here as an NSF fellow at the ITC and working with my friends and me. And then she has a Hubble Fellowship now at Yale, but she also has a faculty job waiting for her at UMass Amherst, where she will go next year. Okay, so there's the pedigree. The story of what is the most important thing about Stella. You probably know that she works on star formation, but the thing I'm going to tell you is that she's very brave. Okay, so most theorists say that they want to compare with observations, and they make the observers come to them. Okay, so they say, here's my theory, turn your observations into something that's physical, and then you can compare with my theory. Stella does the opposite. So Stella will actually make a theory, produce the physical parameters, and then actually observe the simulations as if she was observing them with a real telescope. And she's done these kind of pretend observations with a large range of telescopes, including ALMA. She's had plenty of ALMA time, more than the rest of us. And she's had some fantastic results. And so I like to think of her as a theorist who likes to think like an observer, or at least acknowledges that observations are difficult. And she also has done a tremendous job of doing outreach. So she was, like I said, an NSF fellow, but she's someone who is always very serious about outreach, regardless of the requirement from NSF. And so I'm not sure if she's going to talk about that at all today, but I just think we should all be grateful and inspired by that, too. So thank you, Stella, and go right ahead.
Which is much more worthy and geared toward the synthetic observations that she just talked up, which I'm actually not going to focus on that much today. So I'm already a disappointment here. But all right. So today I'm actually going to be talking about modeling feedback from low-mass stars, specifically radiation outflows and winds. And I'm talking about this, I think, because they get little attention. People who study local star-forming regions care about these things a lot, but most people are thinking about much larger feedback effects. They care about high-mass stars. High-mass stars are very exciting. They die violently. And as a result, we don't hear very much about what low-mass stars do and why that might be important. So today, that's basically what I'm going to be talking about. Now, first, I try to motivate people to pay attention to my talks. So I'm going to start and just say a few words about why you should care specifically about star formation. So of course, you like to understand the formation of our sun and our own solar system, but there are a couple of key questions that get overlooked. So for example, why does our sun have the mass it has? Why doesn't it have a completely different mass? Why is our sun a single star, not a binary or triple star system? Why is it only surrounded by planets? And both these questions actually are related in some context to stellar feedback, which I will talk about. But then we'd also like to connect our star system to the big picture and try and understand how the formation of our sun, which we don't see very much evidence for around now, what we can learn from this by looking at other systems within the galaxy and how that helps us construct a narrative for how our own sun has formed. And this beautiful imagery you see is from a Worldwide Telescope, which I encourage all of you to download and learn more about the universe just from the comfort of right in front of your computer. It's quite awesome. All right. So I'm going to start with Star Formation 101. Now, this traditional picture of star formation is very simple, but it actually goes back to the 80s. And in this picture, there are four main stages of star formation. So first you have a stage of core formation. You form this dense object within a molecular cloud. It becomes gravitationally unstable. And in stage 2, it collapses to form a protostar and a surrounding accretion disk. Okay, so there's this transport of angular momentum that occurs. Now, these cores are magnetized, so at some point you start getting a bipolar outflow. So a lot of the mass that's coming in is energetically entrained and launched right back out and doesn't actually make it onto the star. So the last stage is the fried egg stage. So in this stage is apparently when we have a residual disk and when we begin forming planets. Okay, but even though this picture is still very similar to our understanding today, we really have evolved in certain ways. So the new improved picture, well, first of all, it's in color, which is a vast improvement. And second, it really focuses on connection and how the star formation process is connected across a wide range of scales. So for example, if we start on the galaxy scale, we need the galaxy conditions to understand the formation of individual molecular clouds. So what are their metallicities? What's the background UV field? What are their densities? What are their masses? That's being inherited from larger scale physics. Then within the cloud, we have the formation of dense cores. So and again, these cores are not isolated, so their conditions are in turn connected to the larger physics of this molecular cloud. What is its mean density, its column density, again, in the magnetic field strength, and the metallicity of this cloud, and all these properties. So we can continue down to even smaller scales. We have the formation of this protostar and accretion disk. But again, this is not isolated because the accretion that's occurring is being fed from a much larger scale. And so this accretion process is really being driven from scales that are inherited from the scale of the core. But in this case, this is a very top-down picture. All the arrows are going in one direction, but that's not really the case. There are in fact a number of processes that start on small scales and impact up to much larger scales. So one such process is radiation. So if you have a high mass star, you have radiation pressure, but even these low mass stars can act to heat their environment, okay? And so this scale is maybe within the core scale, certainly the surrounding disk, and maybe up to a parsec depending upon the mass of the star. Then you have these protostellar outflows, or stellar winds. Now these are these very energetic, collimated, magnetically launched outflows which can span several parsecs or even larger, depending. Finally, the most violent is supernovae. So if we form a bunch of stars and we have some massive stars, then at the end, it's game over for the cloud because the energetics of these supernovae will disperse the cloud back into the standard ISM. So in this whole new picture, you should really not think of an isolated case or even top-down or bottom-up processes. Instead, you should be thinking of star formation as a cycle of life. Okay? All right. All right, so in this talk, I'm going to be focusing on the three main forms of feedback that low-mass stars do. So radiation via heating, protostellar outflows, so energetics and how they inject turbulence and energy into the surrounding cloud, and stellar winds, also in terms of how they inject energy. Okay. So to model these three processes, I'm going to turn to the Orion Adaptive Mesh Refinement Code. So numerical models that will allow us to start at the cloud scale and follow all the way down to the formation of a protostar and a protostellar disk. So these are simulations that are adaptive mesh refinement, which means that we can concentrate the refinement in regions of interest. So the smallest scale cells are the regions right around the protostar, so we can follow the formation of accretion disks like this one. So there's a lot of different physics that goes into these simulations, and instead of putting up a bunch of equations, I'll just tell you generally what's going on here. The simulations, we want to capture supersonic turbulence. We want to capture radiation and follow this heating and feedback from stars. Of course, we need gravity if we want to form stars. And we need stars themselves. So these are sync particles. And these sync particles hopefully act as stars, doing the things that stars do. They accrete, they move around, they radiate, and in some of the simulations, they launch a bipolar outflow to take into account the feedback from these stars kinematically. In the second part of the talk, I'll talk about a different kind of star particle, a B star particle which will launch an isotropic line-driven wind. Okay, so I'm going to start with radiation. I'll just wait while everyone reads the... Some of you are slower readers than others, and it'll just take a while. Okay. All right. So what is this radiation of which I speak? So really, this radiation is not external radiation from the surrounding environment. It's very internal radiation coming directly from the formation process. So we can consider what this radiation is doing from the simple formula that tells us about the protostellar luminosity. So there are two components. The first component is photospheric luminosity, this kind of intrinsic luminosity, which encapsulates nuclear burning or Kelvin-Helmholtz contraction as the star contracts down towards the main sequence. The second part is accretion luminosity. So this is the energy that's released through the process of all this mass falling deeply into this potential well and shocking as it accretes onto the surface of the star. So what goes into this are instantaneous protostellar mass, depends upon the current mass of the star, the instantaneous accretion rate and how quickly mass is accreted, the protostellar radius, and then a fudge factor. So this process is not really well determined. And so exactly how much of this energy is radiated away cleanly versus goes on to being advected into the star, going into driving the wind, is not well known. So instead we have this radiative efficiency factor. So where do we get all these numbers? Well, most of them come directly from the simulation. So here is our sync particles. So we know the mass and the accretion rate directly from hydrodynamics of the collapse of these cores and the formation of these sync particles. If we know the mass and accretion rate, then we can map these on to pre-main sequence tracks, and hopefully that will tell us then some idea of what the photospheric luminosity should be and also what the protostellar radius should be for a given object. Finally, for this fudge factor, we have analytic models. And they seem to suggest about 0.75, but maybe up to 1, and some people adopt 0.5, but it's a somewhat uncertain factor. All right. So to understand what this radiation does to the surrounding cloud, it's easiest if I show you a nice three-dimensional volume rendering. As I've learned from Melissa, a nice movie is definitely worth 1,000 images. So throughout this talk, I will actually have somewhat gratuitous use of movies, which I hope you'll appreciate. So what you're seeing here is a turbulent cloud, and this gray is showing you the density scale, and it's picking out a particular density of about a few thousand particles per centimeter cubed. And what you see here is a lot of filamentary structure winding around the cloud, and if you look carefully, you will see that these stars are forming this blue and red, probably within filaments. Now this blue and red is actually showing you the radiation temperature that's being emitted from the star. So the size of that gives you some indication for how much gas is being affected by this radiative feedback. Now if you look carefully, you can see that they actually stand out quite well, but if you look carefully, you can even see that some of these stars are binary stars. So if you peer closely, you can see that in a few cases, there are actually some of these stars that are orbiting one another. I think there's one here. There it goes. And there's definitely one over here somewhere. All right. But what you can see, though, is one of the reasons why people neglected this process for so long, it's because it's very minimal, okay? So the heating for these low-mass stars is very confined to the local neighborhood right around the star, so within the core. So then you might say, well, that's not particularly exciting or important. But it turns out you should care about that for a couple of different reasons. So if you want to understand the collapse of one of these objects or the evolution of disks, both of these processes depend upon the local temperature, okay, the local sound speed. So on one hand, you have this characteristic Jeans length, the length at which an object ceases to become supported by thermal pressure and becomes gravitationally unstable. And this characteristic size scale, which potentially determines the mass of these objects, depends upon the sound speed. Now once you have an object, you also have a surrounding accretion disk And then you want to know if that disk remains stable. The stability of that disk in part depends upon the thermal support within it. So if you have heating, your disks are going to be more stable than if you have a very cold disk. These cold disks may be prone to fragmentation, which could affect the outcome of the star formation process. All right, so the easiest way to look at these things within the simulations is, again, to zoom in on these forming objects and compare cases where you include this heating and in cases where you don't. So we're looking at two different cores on both sides, and here's the log density scale, so you can think of this as isocontours. On the left, we have a case with radiative feedback, and on the right, there's no radiative feedback. So you can see the crosses are marking the formation of where the star is. So what you can see is that one of these is much more violent and dynamical than the other. This one with radiative feedback tends to be more stable. There's a little brief burp there where there's an accretion event, but otherwise the disk is much more smooth, much more well-behaved. You don't see spiral structure here. Now on the other hand, when you have a cold disk, you get a lot more gravitational instability, which manifests in these spiral arms and a lot of the dynamical evolution of the disk that happens. So in cases where you have this instability, then you can get fragmentation, you can get the formation of a binary system, or you can just get a lot of craziness with the accretion history.
Are you showing us just slices through a continuous cloud?
So this is like a volume within the cloud.
But each of these colors represents a slice.
It's density, yeah.
Yeah, so it's like an volumetric isocontour of density. So if you look carefully at the colors, like this white here, you can see you're looking through the white. So it's not really a slice. It's like a contour, and then I choose the opacity of this. And then if I set the opacity to 1, you don't see the disk because you just see the white blob there. So there's a little bit of an art form in setting up these volume renderings so you can see all the different densities through one another. Yeah, in the previous case, you actually saw that these sources actually looked purple, which is because you're seeing both blue and red through one another. So, but anyway, Alyssa could have a whole lecture on how I can improve all of my volume renderings to make them perfect. So I apologize for this, but anyway. All right. All right, so then if we back up to the global simulation, you can then, for example, compare the distribution of stellar masses you get in each case. In the case with radiation, you have a somewhat smoother distribution. But in the case without this radiative heating, where you have these cold disks, they fragment, you end up with this peak here of low-mass objects, this huge excess of brown dwarfs. And so if your goal is to reproduce the IMF, which we think looks kind of like a log normal and doesn't have a huge excess of brown dwarfs, you can see that one of these simulations is reproducing reality a bit better than the others. And in particular, it shows you that this heating, which seemed to be insignificant, is actually having a profound effect on one of the most fundamental outputs of star formation, the IMF. Okay, but then you might say, but wait a minute, there might be too much heating because there are binary star systems. So maybe you're shutting off too much fragmentation and you're not able to form binaries. Well, these simulations actually do still form binaries in some cases. And I'll point out that low-mass stars are much more predominantly single than high-mass stars. And those are the ones I'm modeling, the low-mass stars. But nonetheless, you can actually still get binaries. So if we take the simulation and we plot the separations of all close pairs as a function of time, you can see that there are a number of close pairs that are forming the simulations. And so these things right here are basically forming binaries. So they're fragmenting out here, outside the disk radius, and then they migrate closer dynamically. So in this sense, you actually can form binaries, though they start out being wider than the case if you have disk fragmentation. Not all of these objects end up forming binaries. Some of them actually escape and are unbound. There's just nearby fragmentation. So the point is that when you have this heating, you don't have this wild fragmentation in the disk. All right. So an example of what this turbulent fragmentation looks like that might go ahead and form wide binaries is something like this. So here we have a kind of filamentary region. This is from turbulence. But within this, you get certain condensations that become gravitationally unstable. So as you follow this as a function of time, you do get fragments within filaments or within the core itself, which end up in some cases being bound and migrating closer. And here's a nice observational example of just looking at one thing compared to another. You can see that, which Alyssa hates, but I think she'll forgive me because this is her observation. Now, actually, I wrote a whole paper doing almost synthetic observations on these objects, but I'm not talking about that today. So the take-home message is you can actually form fragmentation, and this is actually on scales you can actually observe with ALMA. So if I'm wrong about this in simulations, and ALMA does not see these, then we'll need to go back to the drawing board again to do new simulations and try and understand what's going on. All right. So if there are no pressing questions on the first third of the talk, I will move on to feedback number 2, protostellar outflows. Now, protostellar outflows are potentially very interesting because they may have a huge kinematic impact on the cloud. So the quote that I've chosen for this one is from Horace Lamb. So Horace Lamb was one of the foremost experts in fluid dynamics. And he said, sometime in the 1800s, when I die and go to heaven, there are 2 matters in which I hope for enlightenment. One is quantum electrodynamics, and the other is a turbulent motion of fluids. And about the former, I am rather optimistic. So he's still right about this, because we don't really have any good analytic theory for turbulence. I think in the intervening years, we've gotten to understand it somewhat better, but still we have to turn to these large-scale numerical simulations in order to actually model the turbulence and how it evolves and what its characteristics are. All right. So turbulence within molecular clouds is everywhere. So here's one of the most beautiful examples of turbulence that I know of. This is the torus molecular cloud. And what they've done in this image is they've taken spectra through the cloud, this is 12CO, and they subdivided the lines into red and blue shifted emission, and then everything in the middle is green. So what you see from looking at this is there's a huge amount of velocity information here. There's a lot of mixing, and there's a ton of structure, which you can see in part for these nice filamentary structures going through the cloud. So you can also see this, without this image, but just looking at these line widths, the line widths are quite broad. They're much larger than the thermal line width. So they're telling you that this gas is moving very rapidly and very violently within the cloud. All right, so taking this information together, you can go ahead and try and plot the velocity or line widths that we observe as a function of some characteristic size. So this was done by Heyer and Brunt in 2004. The black points are Milky Way clouds, and then they're followed down to smaller scales, okay? So you get this nice, very large scaling between line width and size that goes over several orders of magnitude. And the point to recognize is here's the thermal sound speed. So turbulence is manifesting on all scales throughout the cloud. And exactly how that turbulence gets there is one of the main mysteries in star formation. So there are a couple of corollaries that you can try and take away from all of this turbulence. One is that it has to affect star formation in some way. Okay, all these clouds are turbulent, and so there must be some imprint from it. The second is that star formation is inefficient, probably as a result of all this turbulence, because gas that is moving supersonically is not nicely collapsing and forming stars. All right? So these 2 facts are important and give us some motivation for trying to understand what's going on. Now, where do outflows come in? So outflows come in because they're injecting turbulence on scales of maybe a few tenths to a few parsecs. And the thought is that maybe in these clouds that do have star formation, we can inject turbulence using outflows, and this may impact the star formation process and allow clouds to live for longer periods of time and have turbulence over longer periods of their evolution. So certainly clouds that do not have star formation, do not have outflows, have to get their turbulence elsewhere. But it still might be interesting to see how dynamically these outflows might affect the turbulent energy budget of the cloud. All right. So here are two iconic images of protostellar outflows. Here we have HH4647, which is a nice isolated outflow. You can see it's ejecting a very collimated outflow. Here's the star here, and it's on the scales of a few tenths of a parsec. Now, if you then go ahead and have a cluster where you have outflows going everywhere, then you can see that you can actually affect a very large volume of gas. Okay? So the outflows in this image are being shown by this bluish-greenish emission. So this particular region, NGC 1333, has maybe 150 young stellar objects, all of whom are probably launching these outflows. Okay? So these outflows are important then for two reasons. They might interact with a parent core, which may impact the local star formation process. And second, they might interact with the cloud globally. So you're talking about larger scale turbulent effects. All right. So now we would like to actually put these protostellar outflows in simulations. It turns out that these magnetically launched outflows are actually very tricky to model. And the reason is because the launching of these high velocity winds is happening very close to the stellar surface. So if you want to resolve these, one, you need magnetic fields, and two, you need resolution of a stellar radius, which begins to become very computationally prohibitive. Now, there are some stalwart souls who are going ahead and doing this, and Kengo Tomita is one of these people. And so he has this beautiful simulation which is forming a very young protostar. Here's this disk, here are the magnetic field lines wrapping up around and twisting, and then within you see the protostellar outflows being collimated and ejected. Now this lovely calculation, though, is actually only able to run for a year. So I mean, it's probably a year of his life, but also a year of the protostar. So that means that if we want to put this in a simulation, then you basically have to put in some kind of subgrid models. So with this model, we try to reproduce what we think these outflows are doing as much as we can observe them or as much as we can model them, and then hopefully that's a good representation of what's happening. So our model has a characteristic launching velocity of the Keplerian velocity, which depends upon m and r, which we're modeling in the simulation. And then we have to pick some fraction of gas that's being ejected by these outflows, okay? Usually the fraction that people quote is maybe 10% or 30% of the mass that's coming in never makes it onto the star, but is ejected right back out into these collimated winds. Then we also, the final piece is that we have some distribution of momentum, okay? So these outflows tend to be very collimated, so most of the energy is being ejected right up and below along the rotational axis. The nice thing about these models is these are parameters, the collimation angle and the wind fraction are things that we can vary and see how they affect the output. So for those of you who thought about winds before, these are basically trying to represent an X-wind model. All right. So if you zoom in to one of these simulations, here's a nice hybrid volume rendering of what's actually going on within this launching that's happening. So the blue and green contours are actually showing you the protostellar accretion disk. You can actually see it's interesting because there's a slight warp over here on this side and in this side. Now, in the previous simulation, I showed you the radiation and the heating from the protostar, and it was extremely spherical. But now that we have these outflow cavities, they actually sweep up a lot of mass, and the radiation can leak out above and below the poles. So this yellow and white and orange is really tracing the outflow cavities and this heating that's leaking out in these outflow cavities. So this simulation was also done with YT, but we computed the temperature map that you're seeing here with the Hyperion radiative transfer code. All right. So I've done a series of simulations looking at the effects of outflows in clouds, and today I'm going to focus specifically on outflows in cores and what they do. So here's an example simulation. We have an isolated star-forming core. The core has a mass of about 4 solar masses. So this movie is going to show you the column density in x, y, and z directions, and you'll see what happens as the outflow interacts with the core. So you put in some initial turbulence, the core collapses, forms a protostar in the very center, and then the wind immediately begins to launch and interact with the surrounding gas. So the clock here for this core is up here in the top right corner. So what you see that over about 500,000 years, this outflow not only sweeps up an entrained mass, but it actually pulverizes the core. Okay? And so it's ejecting a huge amount of energy into the core, and a lot of the gas is actually swept up and ejected away from the object. Okay, so using simulations like that, we can then see how much mass is actually ejected versus launched versus accreted in these, for these types of outflows. So in this plot, the initial core mass here is at 4 solar masses in red, and this is hot ambient confining gas up here. So the mass that's accreted onto the star is down here in purple. The mass that's launched is up here in blue. And then a large amount of gas never makes it into the star, but is actually ejected from the domain. So that's up here. And that mass turns out to be equal or even more than the mass that ends up making it onto a star. So we do have some observational constraints on this, okay? So one thing people like to define is an early stage of evolution for protostars called stage 0. So this stage is thought to be the main accretion phase of the star. So at this phase, by definition, the protostellar mass is less than the envelope mass. So for these calculations, this stage 0 goes out about 100,000 years. You can say this is indeed the main accretion phase here. One thing you might compare it to is the observed class 0. These things are not quite the same thing, but again, the class 0 phase is thought to be the main accretion phase of the protostar, and instead of using this criterion, which can't be measured, they use the spectral energy distribution, the bolometric temperature of the sources, to characterize it. And it turns out that the length of time for the class 0 phase is about 100,000 years. So at least as far as we can connect one of these two things, the simulations actually seem to be reproducing something of what the observers are measuring. So I ran a number of different studies, varying this wind parameter and this collimation parameter. And in all cases, there are some differences in details. But it turns out that even the collimated wind is very efficient at entraining and injecting material. So all in all, you end up with a star formation efficiency of how much gas actually makes it onto the star of about 40%. So to go back to the mass of our sun, this is telling us that a large amount of mass that might initially be on the core never makes it onto the star. And so, the star formation process, even as you get down to very small scales, is a very inefficient process. All right. So one other interesting thing that observers have noticed is that the opening angle of these outflows that they're observing with these cores seems to depend on stellar age. So very young sources appear to have very collimated outflows, and much older sources seem to have much broader outflow angles. So if you go back to these simulations, you can definitely see that this is what's also going on here. Now, observationally, observers were looking at this because they thought, well, this might be a signature, a window into what is actually happening, this outflow engine that's driving this very energetic outflow. But what these simulations suggest is that it's not actually probing very deeply close to where the engine is actually happening. Instead, it's probing a generic process for how the outflow sweeps up and entrains this gas from the core. So I actually looked at this when I was at the CfA a few years ago, working with a summer student, Eve Lee, and we made these 12 CO synthetic observations of these cores. and then made plots showing the opening angle evolving as a function of time. Now, like the data is very nonlinear, the simulation data is also nonlinear because this is not a nice, smooth process. It's, there's variability in the accretion, there's clumpiness in the core, and so you get a lot of variations. But in total, you end up having an average fit as a function of time that looks very similar to what observers are finding from the data. All right. So now going back to velocities. So we'd like to figure out how much energy is being ejected from this outflow into the surrounding core and how much might go into driving turbulence locally in these regions. So this movie is going to show you the velocity distribution. So this is the initial core at low velocities. Then you'll see a few kilometers per second and a few tens of kilometers per second. So the star forms here. There's a lot of variability in the beginning as we're setting up this disk. You have a lot of clumpy gas. And then you see the outflow forming as very high velocity gas. You can see it's not symmetric above and below, but there's a lot of variation that's happening. Now this corresponds actually to accretion variability of maybe factors of 2 to 3. So that's sufficient to actually create some fairly large scale changes in the outflow. Now over time, you actually see there's more and more higher velocity gas that's happening out here. So as a lot of this core is ejected, this is driving turbulence into this low density medium around the core. So if you look at the velocity dispersion as a function of time, here we start with 0.5 kilometers per second, the turbulence decays, then the star forms about here, and you begin to have the outflow driving velocity, a large amount of turbulence here, and then it kind of levels up to about a standard amount of 1 kilometers per second. All right, so one of the favorite turbulence things that people like to measure is whether the turbulence is solenoidal or non-solenoidal. So most of you might not care about this, but the way you can actually understand what's happening is you want to figure out how much of this energy is into compression, like this clapping monkey, and how much of this turbulence is actually circular and is stirring. So this might actually make a difference. If something is compressive, maybe this turbulence that's being driven will form new stars. If it's stirring, maybe it just keeps injecting energy and keeps more stars from forming. So this might have very different impacts of what's going on in the cloud. All right, so that's enough of that. Yeah, and that monkey's pretty scary too. It also changed the picture, so I think this monkey is friendlier. Okay, so we can look at this ratio. So here's the ratio of the total solenoidal as the stirring to the total compression as a function of time. Now I've chosen the initial turbulence to be solenoidal. So what happens is they actually decay, and we start getting from solenoidal over here below 1 into compressive. So what's happening is gravity is taking over. The turbulence is decaying, and you're starting to get these compressive motions as core is collapsing. Then the star forms, and then it actually goes to this interesting level of 1 to 1. So these simulations, these two motions are almost equal between gravitational compression and the driving of turbulence. If you look at any given view, you might, for example, see more solenoidal motions relative to compression. Now, that's an isolated case, and it may not be true also for an entire cloud. So to check that, we looked at an entire simulation forming a cluster of stars. And then here, we have the average velocity dispersion as a function of time, and then on top of it, the solenoidal component in blue and the non-solenoidal component in red. So here's a case where it's not centrally condensed, it's not globally gravitationally collapsing, and you end up with much more stirring as a result of the outflow turbulence, which is kind of what you'd expect. All right, so just a word about some ongoing work. All of those simulations don't include magnetic fields, which could be important, which could actually either damp the turbulence or enhance it one way or the other. So I'm currently doing some simulations which have a parallel field to the z-axis of about 10 microgauss. And then you can go ahead and zoom in and see the effects of the field lines up top. Here's the protostar. It's launching this outflow. And on the bottom, you can see the velocity vectors. Okay. So these will still not be as ambitious as Kengo's simulations, because we would like to actually run for 500,000 years to see what the evolution is. So we'll probably still have to use this subgrid model. But nonetheless, we can see what the global effects of these fields are on the evolution. All right. So this brings me to the last portion of my talk on stellar winds. So these stellar winds are really going to be winds of intermediate mass stars, of B stars. So I'll talk about how they are different. So the quote that I've chosen here is somewhat to honor Alyssa Goodman, because she started working on this, and it actually was very interesting, and I began to be interested in modeling it. So this quote is from Isaac Newton. He says, "I was like a boy playing on the seashore and diverting myself now and again by finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me." So here, these pebbles and shells are cores and winds. But unlike this quote, I actually disagree with this quote in some sense, because it turns out by studying the details of these smooth cores and of these nice, pretty wind shells, you can actually get at some fundamental truths about how stars form and interact with their environment. Okay. So Alyssa was actually working on this project with collaborators around the time I came to the CfA. So she was in a process of going out and finding these pretty shells along the seashore. But it turns out the sea here was the Perseus molecular cloud. And so the way that she was doing it was through these three-dimensional volume renderings, which are showing you position, and velocity along the line of sight. So when you put things into 3D, you can actually see things in a different way than you might ordinarily see them. And so using this technique, she could go ahead and pick out, shell-like things which were previously not obvious from looking at the data. All right, so here's the entire cloud of Perseus, and here are these different shells that they identified. And they went ahead and added up the mass, momentum, and energy that was being contributed by these shells in Perseus. And what they found was quite interesting. So if you look at the total from bipolar outflows, we're talking about a very small amount of energy relative to the whole cloud budget. But from these shells, maybe you can make up to 50% of the cloud's turbulent energy. So what's causing these shells? So it seems to be that maybe some more evolved stars, or maybe some B stars, have wandered into the cloud, and through their stellar winds, they're injecting energy and carving out pieces of the cloud. And through this process, they may inject a significant amount of energy. So I came back to this recently through a synthetic observation project with Alyssa. And so although I really like these projects, Alyssa can be a very harsh taskmaster. I spent all of this time, or maybe Chris Beaumont spends all of his time, making these synthetic observations, and then, somehow they disagree, which can be very irritating. So, but it still turns out that the way the simulations and observations disagree can be extremely interesting and reveal a lot about what's going on. So here in this study, which Chris posted to Ask Your PH, was accepted was that this week? This week. Yay, all right. So in this project, we are comparing Orion simulations with the distribution of densities and velocities in Perseus. So here we're trying to compare the 12CO data from the simulation in red with the actual distribution from Perseus. So if you look at the distribution of column densities, the simulation observation actually match pretty well. Okay, they look roughly log normal, which is a reasonable thing to expect. But then you go ahead and you actually look at the velocities and find that maybe they sort of agree here, but then there's this excess here. Okay, so there's this excess in the simulations, which might be due to gravity, but there's also this huge amount of excess high velocities here, which seem to be associated with these shells. Now, as a theorist, I tend to say, well, within a factor of 2, this seems pretty good to me, let's move on. But, you can still learn stuff, within these factors of 2, trying to understand, where this velocity is coming from. So to try to get at that, I looked at some simulations and tried to put in some spherically launched winds. So assuming that some B stars have wandered into this simulated cloud and they're now injecting energy, okay? So this is the simplest possible model you could do, okay? So they all have a high velocity, launching velocity of 200 kilometers per second. Now, actual line-driven winds will be launched from the stellar surface at maybe 1,000 kilometers per second. So that is highly annoying to simulations, because anything that moves that fast creates extremely small time step, if not, breaks the code completely. So it turns out these winds actually, you can show that they decelerate quite quickly as they run into the ISM. So I'm pretty happy with my 200 kilometers per second here. And then we distribute a random set of masses within the cloud, and the mass loss goes as the stellar mass times 10 to the minus 7 solar masses per year. So it's not trivial. So in comparison to the data found in Perseus, here are the Perseus mass loss rates, and here is this sub-region containing a small set of these B stars. All right. So again, here's a movie showing the volume rendering with a few kilometers per second to tens of kilometers per second. And you can see these shells expanding quite rapidly into the surrounding cloud. Now, they're not necessarily nice and smooth. They develop some structure, they interact with the gas. But the point is they're interacting and actually starting to look like some of these shells that are observed. So if we want to go ahead and compare with these velocities, we need to do synthetic observations to produce the 12CO, okay? So in the simulations without winds, gravity and without gravity, you get these kind of very symmetric distributions, and you don't get a high velocity tail, okay? There's just nothing creating these extreme outlier velocities. But then if you go ahead and put in these winds, even if you evolve the simulation for 100,000 years, you get enough of this high velocity tail which begins to start looking like this actual observed tail in the real observations. So this potentially has important effects if you want to try and understand the energy budget of the cloud and how these other sources of turbulence and energy might impact the evolution. Now the big question, do these winds actually drive turbulence as we think of turbulence as in terms of compressive motions or solenoidal motions? I think that's a question that will need to be looked at more closely, though we do see from these simulations that you can get significant energy and you can actually offset the total decay of turbulence if you just look at the total velocities in the cloud. All right. So this brings me to my conclusions. The trifecta of radiative feedback, protostellar outflows, and stellar winds. We see in the first part that radiative heating suppresses local fragmentation. It can suppress the formation of brown dwarfs and thus fundamentally impact the distribution of stellar masses that you get. In the second part, we saw that outflows on small scales can reduce stellar masses through entrainment by up to 50% or more. The second part of what these outflows can do is they can replenish turbulent motions locally. They're more than enough to offset the local turbulent decay. And finally, these stellar winds seem to add interesting velocity structure and potentially a lot of turbulence within clouds. And if you have enough of these things, the injection rate that you get is actually comparable to turbulent decay. So these are another source of potential interesting dynamics and energy within clouds. So I'll leave these conclusions here, and I'm willing to take questions. Thank you.
Mike has his hand up first.
Question about the winds. So, did I understand correctly that the B stars in your simulations were not formed in situ, they were just there? So, have you thought about how it would change if they actually formed? And also, from an observational perspective, do we think like B stars and Perseus formed there or wandered there?
So I talked to Alyssa, and I think Alyssa said that the B stars, many of them probably wandered there, but not all of the shells that are observed have obvious candidate sources. So some of them can actually be evolved protostars that have some kind of strong wind. But in this very simple thing, you just assume the B stars wandered there. They have pretty long lifetimes, and they're actually quite abundant, as Alyssa has worked on.
Yeah, some of them look like young stars, the things in the little shell. And then I don't think that many B stars wander into these clouds, but like in Perseus, there's a previous generation of stars. And so the huge shell in Perseus is actually from a previous generation. It's from a cluster that's known, that's older than the Perseus cloud. So it didn't come from very far away.
Have you followed the calculations far enough to have the shells collide?
No, I haven't evolved them that far. I don't know how much, I guess they do kind of overlap there in some of the areas of Perseus, so I could evolve longer. Yes, that would be interesting. And then the important thing is to do the synthetic observation and try and reproduce that position velocity thing that Alicia showed, where she used that to identify shells. That would be really interesting too.
Bill and Charles?
A stellar talk, Stella.
Thank you.
On the outflows, we know that most star-forming regions disperse their dense gas within a couple million years. So I wonder if you could use that fact to constrain your model and require that the sum total of all the outflows in a cluster-forming region disperse the gas within that time frame.
So that would be a little bit hard because that total time would be dependent upon the actual number of stars that form there, as well as the outflow properties. Yeah, so I haven't thought about it quite from that angle. Most people, including myself, as you know, don't evolve these simulations until the cloud is gone. I think simply these codes can't handle that. Or if you do, what happens, as you also know, is your IMF becomes wrong, which is generally something that simulators try to avoid. So that's a secondary problem. But
the
yes,
whole cloud collapses.
yeah, the whole cloud collapses, and most people don't include outflows at all. And so if you do, hopefully that will self-consistently lead you to a correct IMF. But again, the calculations end up being very expensive, so you have that problem. People don't want to do it, but worth doing, yes.
Charles?
So maybe you said this, but it didn't capture what the temperature of the motion of the molecular gas is. And can you actually accelerate that gas without heating it? Because some of these outflow velocities are pretty high.
That's correct. So the bulk temperature is 10 Kelvin of the cloud. Now, the outflow itself is generally thought to be launched as being ionized. So we're talking about 10,000 degree gas of this very high velocity. But nonetheless, you can actually slow down and entrain material at the slower velocity wind. And observers have looked at temperatures of that gas, and they find that it might be, anywhere from tens of Kelvin up to maybe 200 Kelvin or so. So the answer is yes, you can actually sweep up some of this gas without totally shocking it and destroying the CO.
So the clouds can do it. Can you do it?
So that's a good question. So actually, I happily got a nice Yale undergrad to work on this project. So the temperature and the evolution of that is something I haven't looked at, but I've been thinking about. So it's possible I might actually get the answer to that question sometime this year, although very slowly.
Ruth was next.
Did the outflows from the second part of your talk change the results about radiation feedback from the first part?
Yeah, so that's true. So you get an efficiency factor. So if some of your mass is escaping, then you might have lower accretion rates, and then you have different distribution of heating, for example, or you
also
have
just
less
have
heating.
cavities in geometry.
Yes.
Where radiation
That is true. So it does overall lower the effect of heating. And this has been looked at in some cluster simulations also by the Klein and McKee group separately. And what they find is that, yes, it does impact the IMF, but even if you have this heating, you don't then get disfragmentation. So you're still able to suppress and provide thermal support, at least in the very central regions. But yes, different things do happen slightly differently.
So we'll go front and then back.
Since we know that stars don't always accrete smoothly, you can have episodic accretion bursts. I was wondering how that would affect your total star formation efficiency in cores and other aspects of the outflow part.
My understanding is that a lot of the episodic stuff is a late time stuff. It is not necessarily early time stuff. So I don't think it affects the overall masses that you get out. I think it affects the later stage accretion, and it's a very important problem for understanding disk and disk evolution. So the simulations are doing accretion self-consistently insofar that they can. So you do have some gravitational instabilities happening at some time. They tend to be rarer when you have this feedback. But the physics that probably produces these huge bursts, I think, is a magnetic phenomenon. And so that's not included here and is not done correctly in any three-dimensional simulations I know about. So I think that's a future area that simulations need to work on more carefully to try and get right.
After the observational taskmasters make you do it. Go ahead.
I was wondering, you talk about outflows and winds. Where do the jets fit in this picture? Slow jets we can see in other objects too. You had the warp disk and you had the outflow maybe processing with, are there jets?
Yeah, so in a sense, the reason we put in the model is to try to get some of this jet material. Now, the way I did the volume rendering, if I had chosen a higher velocity to show you as one of the contours, you would see it get much narrower. So a lot of the red velocity that you saw in the movies, some of that is part of the jet, but some of it is in-train material. So what I'm saying here is that in the simulations, there's a continuum of velocities. We're launching a high velocity component that is like a jet. But through this process, you get a lot of slower velocity material moving out. One of the fundamental questions, I think, is, are there actually two mechanisms for launching outflows? Are there two different mechanisms? For example, could you launch it from the wind and also have a different mechanism for launching a jet? And that's something that I think people are not really sure about. So these simulations are aimed to try to reproduce both parts, the very high velocity collimated part, and through entrainment, this lower velocity material.
Right now there's, over the last couple of years, there's been a whole cottage industry of the IMF studies in massive galaxies, and there's a hypothesis that the IMF slope in the low mass end actually is related to metallicity. In your case, once you switch on the outflow, you get the IMF cutoff, which can be equivalent to steepening it or making it shallower in terms of modeling. Do you have any parameter in the outflows that you can adjust in order which can be related to the metallicity, which would actually move this cutoff mass back and forth?
So my understanding of the IMF and metallicity is that how the IMF depends on metallicity is not well constructed. So people think that it varies weakly. So these are from simulations that people have been doing, which are like this, and they go ahead and they vary the dust content of the simulation. And so in many cases they find the IMFs, for factor changes of 10 or even 100 changes in metallicity are not hugely different. Now as you go to very low metallicities, then you have to get some difference. But I think people are still kind of arguing about that. From the galactic picture, that is also a very complicated one, in the sense that people, for many years have reported variable IMFs for various different conditions. And I like the talk that Nate Bastian gives about this. Well, first he puts the list of citations where people say the IMF is top-heavy, and that apparently occurred from 2003 to about 2006. And then around 2006 or 2007, people suddenly decided the IMF was bottom-heavy. And there's another column of people that said, well, there's both or neither or whatever. And so as a numericist, I guess I'm a little bit skeptical. I see some kind of more coherence picture that's emerging, that's connecting different sets of observations that are telling us that there is some variation. If you put together lensing and put together the spectral observations that Charlie Conroy has, some of that is starting to look pretty convincing. But because of this very complicated history, there's been lots of arguments. It's like the boy who cried wolf. So now I want to see the wolf before I actually believe that all this variation is going on quite so much.
And then also, isn't it true that the coupling of the gas and the dust and what you actually mean by metallicity is not realistic at all in any simulation?
Yeah.
Apparently do. There was one more.
When you discussed some of the observations, you identified these striations. And so when you see a long correlation length in one direction and short correlation lengths in the other direction, to me it speaks of magnetic fields being important at the largest scales. But is that something you actually believe, or is there something else causing these striations that's not related to a large-scale field?
I think the torus image I showed is a beautiful example of magnetic fields creating structure. Now that said, there's still a lot of arguing in the community about how magnetic fields are important and on what scales. So I don't really think that's a solved problem. I think people are now putting them in, but what is the correct level of field and what is the correct dissipation mechanism for the fields and on what scales does that act? I think that's still being sorted out.
Well, let's thank Stella.